Right, hi everybody. I'm standing between you and coffee, so just bear with me. So thank you very much to the organizers, and I just want to acknowledge my collaborators and colleagues. I'm from the University of Tasmania in Hobart, and in particular mention Leanne Armand, who sadly passed away last year, who was the PI on the voyage that I'm going to describe the cause. And so here you can see we're back in East Antarctica. Here's the Sabrina subglacial basin. Behind it, the much larger Aurora subglacial basin. And so this area is drained predominantly by the Totten Glacier. And we know from observations that this glacier is behaving much more like West Antarctic glaciers than the East Antarctic glaciers. And so today we can see thinning of the ice shelf front, and changes in the grounding line that's been associated predominantly with oceanographic forcing. And so this glacier is really interesting to understand because it contains a huge volume of sea ice that's equivalent to the entire West Antarctic ice sheet. So the changes that we've observed in terms of the velocity of the Totten Glacier and how it's changed through time have been observed to be related to oceanographic changes. So here you can see a plot of temperature on the shelf, and you can see that through time we've observed more intrusions of circumpolar deep water onto the shelf. And this is facilitated by the topography of the shelf, which you can see up here has lots of deep troughs that allow the warmer modified circumpolar deep water to access the ice shelf front and drive that basal melting. So I'm going to show you some data from these cores. I'm not going to present all the data because I only have 10 minutes. But these cores are, there's two cores in the west here in this main depicenter that's related to changes in the supply of terrigenous sediment from the Totten Glacier. We've also got the Moscow University glacier here, and two cores in the east. And so this is a sort of more energetic environment, lots of canyons. And so we're looking at chondrite deposits here. You can see the direction, this westward direction of the Antarctic coastal current, and then the further north, the influence of the ACC. There's also a gyre circulation system here, which is hypothesized to sort of help get the circumpolar deep water up onto the shelf, and that's sort of related to the Antarctic slope current. So we know that weakening of the Antarctic slope current is predicted to increase through time, and that's modeling results have shown that that'll actually drive further basal melting because the Antarctic coastal current or slope front, sort of creates a bathymetric, an oceanographic separation between the warm Southern Ocean waters and the cooler shelf waters. So as many of you in the room are experienced with, developing age models in Antarctic sediment cores is difficult and really painful. And so I'm happy to discuss the age models, but basically the radiocarbon dated acid insoluble organic matter, and we used the surface ages of some multi-cores to get rid of some of this older recycled carbon that hangs around and makes the ages incredibly old. And then we used bacon to give us some statistically meaningful age model. And so I'm just going to show the results for KCO2. So that's one of the core sites that's in the west, nearest to the Totten Glacier, in this main fan of sediment. And immediately, and basically the other core sites, they show very similar trends in the different proxies, but obviously at different depths. I'm just going to work in depth space for the moment. And what I want you to have a look at here is the sedimentation rates. And so in the glacial sediments, you can see we've got incredibly high sediment accumulation of about 35 centimeters per 1,000 years. And then that changes rapidly into the Holocene, and they're about 7 times lower in the Holocene. And so one of the objectives was to use ice rafted debris flux to look at how the Antarctic ice sheet has changed through time. But when actually calculating the IRD flux, the signal is sort of totally overrun by this huge change in sediment accumulation rate. So we're just looking here at the coarse sand fraction, so that's the amount of 250 microns to 2 millimeter grain sizes that relate to, in this case, what we think is obviously ice rafted debris supply, but also the proximity of the grounding line, which we know from previous studies on the shelf was much closer to the shelf break during the glacial period. So the glacial sediment units have higher coarse sand fraction, which if we go to the next proxy is looking at extinct diatoms. We also see a high proportion of extinct and robust diatom species in the glacial units. And again, this is because the ice, the grounding line has sort of pushed and bulldozed itself across the shelf and supplies this high terrigenous sediment, but also extinct and reworked diatoms from the shelf. And you can see this shift in extinct diatoms. Here we did some Bayesian change point analysis, so I wasn't sort of picking where the deglaciation was by eye. And so the first change that we see in the records is this decrease in extinct diatoms, followed by a decrease in ice rafted debris. And so these data are interpreted to tell us about when the sort of end of the maximum glaciation on this margin was prior to the retreat phase. And so the retreat phase is interpreted based on the proportion of clay in the sediment. So you can see, if I go back, we see a change again around 100 centimeters depth. We have this shift from about 60 to 30% clays. And this is interpreted as a reduction in the supply of terrigenous materials. So actually the grounding line retreating south and the sediment being trapped on the shelf and not supplying that high sediment accumulation to the continental rise. So for provenance work, we did some neodymium and strontium isotopes on all the core sites, and we see a really consistent signature through time. So there's no changes in the provenance of sediment as the grounding line retreats south. And this isn't surprising given the orientation, which I'm not showing you here. The orientation of the provinces beneath the grounding line are perpendicular, and so they're not particularly helpful in helping us distinguish exactly where the grounding line is, because they jut out in the seaward direction. And you would have to go back about 500 kilometers to see any changes in the geological provinces beneath the ice sheet, which is obviously not happening from the cold glacial period to the warm Holocene. So we see, following this change in the supply of clays from the ice sheet, we see an increase in the diatoms and an increase in the sortable silt percent. So Gisela introduced the sortable silt proxy, so this is our proxy for increases in current strength. So bringing this all together to try and make some assessment with all four cores, with some sort of like weary assignment of age given the errors associated with the age models. What we can say is that the ice sheet reached its maximum extent between 21 and 18,000 years ago, and that's evidenced by the extinct diatoms and the ice rafted debris. And this change in the retreat of the ice sheet happens following that around 15 to 18,000 years ago. And this is sort of at the same time that we see large changes in the climate associated with Heinrich Stadial 1. but it's not associated with increases in Antarctic temperature and carbon dioxide. The retreat phase is sort of happening at the same time as the rest of the climate is deglaciating. And so part of that, what we think, sorry, I'll skip on a bit quicker, is that this ice margin is responding to changes in sea ice, and it's actually changes in sea ice and insulation forcing that and that sort of drives changes in the ice sheet on this margin. And so this can be hypothesized by some really nice modeling by Rafael Ferrari, which shows us how the position of the sea ice is what's controlling the access for circumpolar deep water to the margin. So here in the glacial period, when sea ice was further north, the isopycnal, where the water's upwell, is further north and shifted away, and this allowed the upper and the lower cell of the circulation system to be separated. And then when the climate warmed and when insulation drove ice sheet retreat further south, this isopycnal then moves further south and allows circumpolar deep water to access closer to the Antarctic margin. So the main sort of takeaway from this talk is that the Sabrina ice margin is really sensitive to changes in climate forcing, it's not surprising given what we can see today in the current oceanographic and ice sheet changes. Thanks.
We have time for a question. Tina, you're making me run.
Hi, Tina.
Sorry to make you run. Awesome talk, Taryn. I was wondering whether you've any success in finding any proxies for the circumpolar deep water in the area to actually link the mechanism you proposed to the data?
Yes, of course, the big gap that I don't have. Tina, I was talking with Peter Beil because he took some samples and he was going to have a look. So what I understand is that doing organic temperature-based proxy work, less than 1 million-year-old sediment, and it's not easy. I know that Amelia Chevenel's group has some success with some cores on the shelf, and they actually see very similar results in terms of the timing. The age models are independent. They have much better sort of ramp pyrolysis dates, and they do see evidence in terms of their GDDTs for warmer circumpolar deep waters coming up onto the shelf, and this very rapid retreat phase. Yes, there is evidence. There's also sea ice evidence. Henrik Sadesky has a really nice paper that's coming out soon that actually uses the, I can't remember, the HBI's sea ice proxy on KC12. So although I've sort of shown half the data, I'm talking about the full story, and I haven't really presented all the data because it's sort of everybody's data. Thanks, Tina.
Thank you. Right, we'll stop there. I just want to say thank you very much to our speakers for an amazing set of talks, intriguing data.